All right, let's dive right into this explainer. Today, we are tackling some truly complex classical mechanics. We're going to derive every single formula from chapters 1 through 4, and we're doing it without skipping a single mathematical step. If you've ever felt totally lost because a textbook casually threw in therefore it is obvious that, well, you are absolutely in the right place. Let's follow the math together.
Here's our roadmap for today. 1. The rigorous problem framework. 2. Deriving one-dimensional kinematics. 3. Mastering two-dimensional trajectories. 4. Dynamics and non-inertial frames. And finally, 5. The power of rigor. By escalating the mathematical complexity and actually seeing every step, we're going to build the intuition you need to solve virtually any problem.
Section 1. The rigorous problem framework. Derivations without compromise.
We're kicking things off with a foundational rule for this explainer. Absolutely no hand-waving the math. As the source text points out, the real magic in physics happens in the margins. It's where variables are defined and assertions are rigorously justified. When you emphasize progressive derivations and build equations step by step from first principles, you aren't just memorizing formulas, you're literally learning the language of the universe.
Moving right along to Section 2, Deriving One-Dimensional Kinematics, Integrating Acceleration. So let's look at our first escalation covering the core concepts of chapters 1 and 2. Now look at this seemingly simple problem. It actually requires strict integration rather than standard algebra, because our acceleration is 6 times t, meaning it actually increases as time goes on. Our standard, high school kinematic equations completely fall apart here. We have to use calculus.
Okay, let's step through the velocity derivation. We start with the fundamental definition. Acceleration is the derivative of velocity. So, to work backward, we integrate. We carefully pull our initial velocity of 2 meters per second out as a constant, and then we execute the integral over our variable acceleration, 6t. Now, the integral of t is 1/2 t squared, which leaves us with a beautiful exact velocity function. v of t equals 2 plus 3t squared.
Continuing that logic, we just plug our newly derived velocity function right into the position integral to finalize these one-dimensional exercises. Our initial position is 0. We integrate the function 2 plus 3t squared. That constant 2 becomes 2t, and 3t squared integrates perfectly up to t cubed. So our final exact position function is 2t plus t cubed. No wild assumptions here, just pure derived math.
Section 3. Mastering two-dimensional trajectories and the independence of axes.
The crucial point now is scaling this up. Life rarely moves in just a straight line, right? Before we jump into the algebra for Chapter 3, let's visually anchor ourselves with this textbook diagram mapping an independent x and y curve. When a projectile flies through the air, it's actually doing two completely separate things at exactly the same time, moving horizontally and falling vertically. Our goal here? We want to extract the exact velocity and acceleration vectors from this polynomial soup using component decomposition. Notice that I and j notation? That tells us exactly what belongs to the horizontal x-axis and what belongs to the vertical y-axis.
This breakdown brilliantly illustrates the absolutely core rule of 2D kinematics. Perpendicular axes are mathematically completely independent. We treat the x-axis and y-axis as two entirely separate problems. By taking the time derivative of the x component, we get the horizontal velocity, 4t minus 3. Deriving the y component gives us the vertical velocity, 3t squared minus 8t. They do not mix.
Now, if we take the next derivative step on our velocity components, we find our x acceleration is constant at 4 meters per second squared. But take a look at our y acceleration. It's surprisingly variable, dropping down to 6t minus 8. The math is telling us exactly how this particle is behaving in space at every possible fraction of a second.
These snapshots from the source text prove that the vector methods we just utilized fundamentally rebuild the kinematic equations from the ground up. By starting with vector definitions of acceleration and integrating them across separate axes, we naturally arrive at the universal kinematic formulas. It's just really elegant to see it derive out so cleanly.
All right, Section 4. Dynamics and non-inertial frames. Forces at play.
Let's combine our kinematic tools with Newtonian dynamics, stepping into Chapter 4's most complex derivations. Now that we know how things move, we introduce the forces that cause them to move. Let's ground our math in reality again. What we're looking at here is a baseline free body diagram showing a simple tension versus weight equilibrium.
It's a mass hanging on a string. Gravity pulls down with force, m times g, and the string pulls up with tension, T. In a stationary room, these perfectly cancel out. The net force is 0.
But man, things get wild when the system itself starts accelerating. Let's drive exactly how that string reacts. Imagine this pendulum is hanging from the ceiling of an elevator, and suddenly, the elevator lurches horizontally to the right at 4.0 meters per second squared. The pendulum is going to swing backward for sure, but at what exact angle, and how much tighter does that string get?
Looking directly at the textbook solution for this exercise, we see a huge need to define our observer's frame of reference. The math literally changes, depending on whether you were standing inside the moving elevator or watching from the solid ground outside. This comparison is honestly fascinating. If you are in the elevator, a non-inertial frame, you feel a mysterious, invisible force pushing the pendulum backward. To make the math work, we have to insert a fictitious force equal to negative mass times the frame's acceleration. But if you are on the ground, an inertial frame, there is no magic force. You simply use Newton's second law, the sum of the forces equals mass times acceleration. And miraculously, the fictitious force mathematically mimics the standard mass acceleration term perfectly. They yield the exact same core equations.
So armed with those frame-agnostic equations, let's derive the angle of the pendulum. We divide the x-axis force equation by the y-axis force equation. Because tension T is in both, it brilliantly cancels out. Sine theta divided by cosine theta perfectly isolates the tangent function, so tangent theta simply equals the elevator's acceleration divided by gravity. 4.0 divided by 9.8 gives us an exact angle of 22.2 degrees.
Finally, we take that exact angle and just back-substitute it into our y-axis equation to definitively calculate the tension down to the second decimal. The mass is 0.5 kilograms, gravity is 9.8. We divide that product by the cosine of 22.2 degrees. The tension works out to exactly 5.29 newtons. The string doesn't just hang there anymore. It is actively supporting both the weight and the horizontal acceleration.
Section 5. The power of rigor. Okay, let's bring it all together and see what we've gained from this meticulous mathematical marathon through chapters 1 to 4. By enforcing strict derivation steps, we've basically unlocked core mechanical truths that shortcuts would have totally hidden from us. We proved that integrating acceleration is the only way to handle variable motion. We proved that multidimensional problems are just one-dimensional problems stacked together, and we proved that physics remains true whether you are standing still or accelerating in a metal box.
As the Chapter 4 summary points out, putting in the hard work on these fundamental steps literally prepares you for anything the physical universe throws your way. The rigorous math isn't just busy work, it is the absolute foundation of understanding.
I'm going to leave you to ponder that exact question as you continue your journey through advanced physics. When math models reality this perfectly, the line between an abstract equation and a physical truth gets incredibly blurry. Thanks for joining me on this explainer, and keep questioning those formulas.